We now pass to the discussion of the fundamental principles of dynamics. This is entirely a modern science. The mechanical speculations of the ancients, particularly of the Greeks, related wholly to statics. Dynamics was founded by Galileo. We shall readily recognize the correctness of this assertion if we but consider a moment a few propositions held by the Aristotelians of Galileo's time. To explain the descent of heavy bodies and the rising of light bodies, in liquids for instance, it was assumed that every thing and object sought its place. The place of heavy bodies was below, the place of light bodies was above. Motions were divided into natural motions, as that of descent, and violent motions, as, for example, that of a projectile. From some few superficial experiments and observations, philosophers had concluded that heavy bodies fall more quickly and lighter bodies more slowly, or, more precisely, that bodies of greater weight fall more quickly and those of less weight more slowly. It is sufficiently obvious from this that the dynamical knowledge of the ancients, particularly of the Greeks, was very insignificant, and that it was left to modern times to lay the true foundations of this department of inquiry. The treatise Discorsi e Dimostrationi Mathematica, in which Galileo communicated to the world the first dynamical investigation of the laws of falling bodies, appeared in 1638. The modern spirit that Galileo discovers is evidenced here at the very outset by the fact that he does not ask why heavy bodies fall, but propounds the question, how do heavy bodies fall? In agreement with what law do freely falling bodies move? The method he employs to ascertain this law is this. He makes certain assumptions. He does not, however, like Aristotle, rest there, but endeavors to ascertain by trial whether they are correct or not. The first theory on which he lights is the following. It seems in his eyes plausible that a freely falling body, inasmuch as it is plain that its velocity is constantly on the increase, so moves that its velocity is double after traversing double the distance, and triple after traversing triple the distance. In short, that the velocities acquired in the descent increase proportionally to the distances descended through. Before he proceeds to test experimentally this hypothesis, he reasons on it logically, implicates himself, however, in so doing, in a fallacy. He says, if a body has acquired a certain velocity in the first distance descended through, double the velocity in double such distance descended through, and so on. That is to say, if the velocity in the second instance is double what it is in the first, then the double distance will be traversed in the same time as the original simple distance. If, accordingly, in the case of the double distance, we conceive the first half traversed, no time will, it would seem, fall to the account of the second half. The motion of a falling body appears, therefore, to take place instantaneously, which not only contradicts the hypothesis but also overthrows it entirely. This is the peculiar fallacy of that assumption. After Galileo fancied he had discovered this assumption to be untenable, he made a second one, according to which the velocity acquired is proportional to the time of the descent. That is, if a body fall once and then fall again during twice as long an interval of time as it first fell, it will attain in the second instance double the velocity it acquired in the first. He found no self-contradiction in this theory, and he accordingly proceeded to investigate by experiment whether the assumption accorded with observed facts. It was difficult to prove by any direct means that the velocity acquired was proportional to the time of descent. It was easier, however, to investigate by what law the distance increased with the time, and he consequently deduced from his assumption the relation that obtained between the distance and the time, and tested this by experiment. The deduction is simple, distinct, and perfectly correct. He draws, in figure 87, a straight line, and on it cuts off successive portions that represent to him the times elapsed. At the extremities of these portions, he erects perpendiculars called ordinates, and these represent the velocities acquired. Any portion OG of the line OA denotes, therefore, the time of descent elapsed, and the corresponding perpendicular GH the velocity acquired in such time. If now we fix our attention on the progress of the velocities, we shall observe with Galileo the following fact. Namely, that at the instant c, at which 1/2 of OC of the time of descent OA has elapsed, the velocity CD is also 1/2 of the final velocity AB. And again, if we compare equal distances in opposite directions from the instant C, we shall observe that the velocity hg exceeds the mean velocity cd by the same amount that ef falls short of it. For every instant antecedent to c, there exists a corresponding one equally distant from it subsequent to c. Whatever loss, therefore, as compared with uniform motion with half the final velocity, is suffered in the first half of the motion, such loss is made up in the second half. The distance fallen through we may consequently regard as having been uniformly described with half the final velocity. If, accordingly, we make the final velocity proportional to the time of descent t, we shall obtain v equals g times t, where g denotes the final velocity acquired in unit of time, the so-called acceleration. The space s descended through is therefore given by the equation s equals gt over 2 multiplied by t, or s equals gt squared over 2. Motion of this sort, in which, agreeably to the assumption, equal velocities constantly accrue in equal intervals of time, we call uniformly accelerated motion. If we collect the times of descent, the final velocities, and the distances traversed, we shall obtain the following table. For time 1, the velocity is 1 times g, and the space is 1 times g over 2. For time 2, the velocity is 2 times g, and the space is 2 squared times g over 2. For time 3, the velocity is 3 times g, and the space is 3 squared times g over 2. For time 4, the velocity is 4 times g, and the space is 4 squared times g over 2. In general, for time t, the velocity is t times g, and the space is t squared times g over 2. The relation obtaining between time and space admits of experimental proof, and this Galileo accomplished in the manner which we shall now describe. We must first remark that no part of the knowledge and ideas on this subject with which we are now so familiar existed in Galileo's time, but that Galileo had to create these ideas and means for us. Accordingly, it was impossible for him to proceed as we should do today, and he was obliged, therefore, to pursue a different method. He first sought to retard the motion of descent, that it might be more accurately observed. He made observations on balls which he caused to roll down inclined planes or grooves, assuming that only the velocity of the motion would be lessened here, but that the form of the law of descent would remain unmodified. If, beginning from the upper extremity, the distances 1, 4, 9, 16, and so forth, be notched off on the groove, the respective times of descent will be representable, it was assumed, by the numbers 1, 2, 3, 3, 4, and so forth, a result which was, be it added, confirmed. The observation of the times involved Galileo accomplished in a very ingenious manner. There were no clocks of the modern kind in his day. Such were first rendered possible by the dynamical knowledge of which Galileo laid the foundations. The mechanical clocks which were used were very inaccurate and were available only for the measurement of great spaces of time. Moreover, it was chiefly water clocks and sand glasses that were in use in the form in which they had been handed down from the ancients. Galileo now constructed a very simple clock of his kind, which he especially adjusted to the measurement of small spaces of time, a thing important for our present days. It consisted of a vessel with at the bottom a minute orifice, which was closed with the finger. As soon as the ball began to roll down the inclined plane, Galileo removed his finger and allowed the water to flow out on a balance. When the ball had arrived at the terminus of its path, he closed the orifice. As the pressure height of the fluid did not, owing to the great transverse dimensions of the vessel, perceptibly change, the weights of the water discharged from the orifice were proportional to the times. It was in this way actually shown that the times increased simply, while the spaces fallen through increased quadratically. The inference from Galileo's assumption was thus confirmed by experiment, and with it the assumption itself. To form some notion of the relation which subsists between motion on an inclined plane and that of free descent, Galileo made the assumption that a body which falls through the height of an inclined plane attains the same final velocity as a body which falls through its length. This is an assumption that will strike us as rather a bold one, but in the manner in which it was enunciated and employed by Galileo, it is quite natural. We shall endeavor to explain the way by which he was led to it. He says, if a body fall freely downwards, its velocity increases proportionally to the time. When then the body has arrived at a point beneath, let us imagine its velocity reversed and directed upwards. The body then, it is clear, will rise. We make the observation that its motion in this case is a reflection, so to speak, of its motion in the first case. As then its velocity increased proportionally to the time of descent, it will now, conversely, diminish in the same proportion. When the body has continued to rise for as long a time as it descended and has reached the height from which it originally fell, its velocity will be reduced to zero. We perceive, therefore, that a body will rise, in virtue of the velocity acquired in its descent, just as high as it has fallen. If, accordingly, a body falling down an inclined plane could acquire a velocity which would enable it, when placed on a differently inclined plane, to rise higher than the point from which it had fallen, we should be able to effect the elevation of bodies by gravity alone. There is contained, accordingly, in this assumption, that the velocity acquired by a body in descent depends solely on the vertical height fallen through and is independent of the inclination of the path, nothing more than the contradictory apprehension and recognition of the fact that heavy bodies do not possess the tendency to rise, but only the tendency to fall. If we should assume that a body falling down the length of an inclined plane in some way or other attained a greater velocity than a body that fell through its height, we should only have to let the body pass with the acquired velocity to another inclined or vertical plane to make it rise to a greater vertical height than it had fallen from. And if the velocity attained on the inclined plane were less, we should only have to reverse the process to obtain the same result. In both instances, a heavy body could, by an appropriate arrangement of inclined planes, be forced continually upwards solely by its own weight, a state of things which wholly contradicts our instinctive knowledge of the nature of heavy bodies. In this case, again, Galileo did not stop with the mere philosophical and logical discussion of his assumption, but tested it by comparison with experiment. The experiment illustrated in Figure 88 exhibits the case of a heavy metal one. However, this neglected, the body ascends to the same altitude on the opposite side. If it does not do so exactly, Galileo said, the resistance of the air must be the cause of the deficit. This is inferable from the fact that the deficiency is greater in the case of a cork ball than it is in the case of a heavy metal one. Now, it is permissible to regard the motion of a pendulum in the arc of a circle as a motion of descent along a series of inclined planes of different inclinations. This seen, we can, with Galileo, easily cause the body to rise on a different arc, on a different series of inclined planes. This we accomplish by driving in at one side of the thread as it vertically hangs, a nail which will prevent any given portion of the thread from taking part in the second half of the motion. The moment the thread arrives at the line of equilibrium and strikes the nail, the ball, which has fallen through, will begin to ascend by a different series of inclined planes and describe the arc AM or AN. Now, if the inclination of the planes had any influence on the velocity of descent, the body could not rise to the same horizontal level from which it had fallen. But it does. By driving the nail sufficiently low down, we may shorten the pendulum for half of an oscillation as much as we please. The phenomenon, however, always remains the same. If the nail be driven so low down that the remainder of the string cannot reach to the plane E, the ball will turn completely over and wind the thread round the nail, because when it has attained the greatest height it can reach, it still has a residual velocity left. If we assume thus that the same final velocity is attained on an inclined plane, whether the body fall through the height or the length of the plane, in which assumption nothing more is contained than that a body rises by virtue of the velocity it has acquired in falling just as high as it has fallen, we shall easily arrive with Galileo at the perception that the times of the descent along the height and the length of an inclined plane are in the simple proportion of the height and the length, or, what is the same, that the accelerations are inversely proportional to the times of descent. The acceleration along the height will consequently bear to the acceleration along the length the proportion of the length to the height. Let AB be the height and AC the length of the inclined plane. Both will be described through in uniformly accelerated motion in the times t and t1 with the final velocity v. Therefore, AB equals 1 half gt squared, and AC equals 1 half g1t1 squared. Hence, the ratio g over g1 equals t1 over t equals AB over AC, which equals sine alpha. In this way, we are able to deduce from the acceleration on an inclined plane the acceleration of free descent. From this proposition, Galileo deduces several corollaries, some of which have passed into our elementary textbooks. The accelerations along the height and length are in the inverse proportion of the height and length. If now we cause one body to fall along the length of an inclined plane and simultaneously another to fall freely along its height, and ask what the distances are that are traversed by the two in equal intervals of time, the solution of the problem will be readily found by simply letting fall from B a perpendicular on the length. The part AD, thus cut off, will be the distance traversed by the one body on the inclined plane, while the second body is freely falling through the height of the plane. If we describe a circle on AB as diameter, the circle will pass through D because D is a right angle. It will be seen thus that we can imagine any number of inclined planes of any degree of inclination passing through A, and that in every case the chords AG, AH, drawn in this circle from the upper extremity of the diameter, will be traversed in the same time by a falling body as the vertical diameter itself. Since obviously only the lengths and inclinations are essential here, we may also draw the chords in question from the lower extremity of the diameter, and say generally the vertical diameter of a circle is described by a falling particle in the same time that any chord through either extremity is so described. We shall present another corollary which, in the pretty form in which Galileo gave it, is usually no longer incorporated in elementary expositions. We imagine gutters radiating in a vertical plane from a common point A at a number of different degrees of inclination to the horizon. We place at their common extremity A a like number of heavy bodies and cause them to begin simultaneously their motion of descent. The bodies will always form at any one instant of time a circle. After the lapse of a longer time, they will be found in a circle of larger radius, and the radii increase proportionally to the squares of the times. If we imagine the gutters to radiate in space instead of a plane, the falling bodies will always form a sphere, and the radii of the spheres will increase proportionally to the squares of the times. This will be perceived by imagining the figure revolved about the vertical AV. We see thus, as deserves again to be briefly noticed, that Galileo did not supply us with a theory of the falling of bodies, but investigated and established wholly without preformed opinions the actual facts of falling. Gradually adapting, on this occasion, his thoughts to the facts, and everywhere logically abiding by the ideas he had reached, he hit on a conception which to himself, perhaps less than to his successors, appeared in the light of a new law. In all his reasonings, Galileo followed, to the greatest advantage of science, a principle which might appropriately be called the principle of continuity. Once we have reached a theory that applies to a particular case, we proceed gradually to modify in thought the conditions of that case, as far as it is at all possible, and endeavor in so doing to adhere throughout as closely as we can to the conception originally reached. There is no method of procedure more surely calculated to lead to that comprehension of all natural phenomena, which is the simplest and also attainable with the least expenditure of mentality and feeling. A particular instance will show more clearly than in any general remarks what we mean. Galileo considers a body which is falling down the inclined plane AB. If it ascend with the velocity thus acquired on a second plane BC, for example, ascends this second plane. On all planes BC, BD, and so forth, it ascends to the horizontal plane that passes through A. But just as it falls on BD with less acceleration than it does on BC, so similarly it will ascend on BD with less retardation than it will on BC. The nearer the planes BC, BD, BE, BF approach the horizontal plane BH, the less will the retardation of the body on those planes be, and the longer and further will it move on them. On the horizontal plane BH, the retardation vanishes entirely. That is, of course, neglecting friction and the resistance of the air, and the body will continue to move infinitely long and infinitely far with constant velocity. Thus, advancing to the limiting case of the problem presented, Galileo discovers the so-called law of inertia, according to which a body not under the influence of forces, in other words, of special circumstances that change motion, will retain forever its velocity and direction. The motion of falling that Galileo found actually to exist is, accordingly, a motion of which the velocity increases proportionally to the time, a so-called uniformly accelerated motion. It would be an anachronism and utterly unhistorical to attempt, as is sometimes done, to derive the uniformly accelerated motion of falling bodies from the constant force of gravity. Gravity is a constant force. Consequently, it generates in equal elements of time equal increments of velocity. Thus, the motion produced is uniformly accelerated. Any expression such as this would be unhistorical and would put the discovery in a false light, for the real reason of the motion of descent, as revealed to us today, was first discovered by Galileo. Before Galileo, force was known solely as pressure. Now, no one can know, who has not learned it from experience, that generally pressure produces motion, much less in what manner pressure passes into motion, that not position nor velocity, but acceleration is determined by it. This cannot be philosophically deduced from the conception itself. Conjectures may be set up concerning it, but experience alone can definitively inform us with regard to it. It is not by any means self-evident, therefore, that the circumstances which determine motion, that is, forces, immediately produce accelerations. A glance at other departments of physics will at once make this clear. The differences of temperature of bodies also determine alterations. However, by differences of temperature, not compensatory accelerations are determined, but compensatory velocities. That it is accelerations which are the immediate effects of the circumstances that determine motion, that is, of the forces, is a fact which Galileo perceived in the natural phenomena. Others before him had also perceived many things. The assertion that everything seeks its place also involves a correct observation. The observation, however, does not hold good in all cases, and it is not exhaustive. If we cast a stone into the air, for example, it no longer seeks its place, since its place is below. But the acceleration towards the earth, the retardation of the upward motion, the fact that Galileo perceived is still present. His observation always remains correct. It holds true more generally. It embraces in one mental effort much more. We have already remarked that Galileo discovered the so-called law of inertia quite incidentally. A body on which, as we are wont to say, no force acts, preserves its direction and velocity unaltered. The fortunes of this law of inertia have been strange. It appears never to have played a prominent part in Galileo's thought. But Galileo's successors, particularly Huygens and Newton, formulated it as an independent law. Nay, some have even made of inertia a general property of matter. We shall readily perceive, however, that the law of inertia is not at all an independent law, but is contained implicitly in Galileo's perception that all circumstances determinative of motion or forces produce accelerations. In fact, if a force determine not position, not velocity, but acceleration, change of velocity, it stands to reason that where there is no force, there will be no change of velocity. It is not necessary to enunciate this in independent form. The embarrassment of the neophyte, which also overcame the great investigators in the face of the great mass of new material presented, alone could have led them to conceive the same fact as two different facts, and to formulate it twice. In any event, to represent inertia as self-evident, or to derive it from the general proposition that the effect of a cause persists, is totally wrong. Only a mistaken straining after rigid logic can lead us so out of the way. Nothing is to be accomplished in the present domain with scholastic propositions like the one just cited. We may easily convince ourselves that the contrary proposition, cessante causa cessat effectus, is as well supported by reason. If we call the acquired velocity the effect, then the first proposition is correct. If we call the acceleration the effect, then the second proposition is correct, which is also Galileo's. Let us proceed to notions familiar to his time, notions developed mainly in the practical arts. One notion of this kind was that of velocity, which is very readily obtained from the consideration of a uniform motion. If a body traverse in every second of time the same distance c, the distance traversed at the end of t seconds will be s equals c times t. The distance c traversed in a second of time we call the velocity, and obtain it from the examination of any portion of the distance and the corresponding time by the help of the equation c equals s over t. That is, by dividing the number, which is the measure of the distance traversed, by the number, which is the measure of the time elapsed. Now, Galileo could not complete his investigations without tacitly modifying and extending the traditional idea of velocity. Let us represent for distinctness' sake in figure 94, in 1, a uniform motion, in 2, a variable motion, by laying off as abscissae in the direction OA the elapsed times, and erecting as ordinates in the direction AB the distances traversed. Now, in 1, whatever increment of the distance we may divide by the corresponding increment of the time, in all cases we obtain for the velocity the same value. But if we were thus to proceed in 2, we should obtain widely differing values, and whether we should regard velocity as ordinarily understood coalesces in this case to be unequivocal. If, however, we take a small element of time where the element of the curve in 2 approaches to a straight line, we may regard the increase as uniform. The velocity in this element of the motion we may then define as the quotient delta s over delta t of the element of the time into the corresponding element of the distance. Still more precisely, the velocity at any instant is defined as the limiting value which the ratio delta s over delta t assumes as the elements become infinitely small, a value designated by ds over dt. This new notion includes the old one as a particular case, and is moreover immediately applicable to uniform motion. Although the express formulation of this idea as thus extended did not take place till long after Galileo, we see nonetheless that he made use of it in his reasonings. An entirely new notion to which Galileo was led is the idea of acceleration. In uniformly accelerated motion, the velocities increase with the time, agreeably to the same law as in uniform motion, the spaces increase with the times. If we call v the velocity acquired in time t, then v equals g times t. Here g denotes the increment of the velocity in unit of time, or the acceleration, which we also obtain from the equation g equals v over t. When the investigation of variably accelerated motions was begun, this notion of acceleration had to experience an extension similar to that of the notion of velocity. If in 1 and 2 the times be again drawn as abscissae, but now the velocities as ordinates, we may go through anew the whole train of the preceding reasoning and define the acceleration as dv over dt, where dv denotes an infinitely small increment of the velocity and dt the corresponding increment of the time. In the notation of the differential calculus we have for the acceleration of a rectilinear motion, phi equals dv over dt, which equals d squared s over dt squared. The ideas here developed are susceptible, moreover, of graphic representation. If we lay off the times as abscissae and the distances as ordinates, we shall perceive that the velocity at each instant is measured by the slope of the curve of the distance. If in a similar manner we put times and velocities together, we shall see that the acceleration of the instant is measured by the slope of the curve of the velocity. The course of the latter slope is, indeed, also capable of being traced in the curve of distances, as will be perceived from the following considerations. Let us imagine, in the usual manner shown in figure 95, a uniform motion represented by a straight line OCD. Let us compare this with a motion OCE, the velocity of which in the second half of the time is greater, and another motion OCF, of which the velocity is in the same proportion smaller. In the first case, accordingly, we shall have to erect for the time OB equals 2OA, an ordinate greater than BD equals 2AC. In the second case, an ordinate less than BD. We see thus, without difficulty, that a curve of distance convex to the axis of the time psi corresponds to accelerated motion, and a curve concave thereto to retarded motion. If we imagine a lead pencil to perform a vertical motion of any kind, and in front of it during its motion a piece of paper to be uniformly drawn along from right to left, and the pencil to thus execute the drawing in figure 96, we shall be able to read off from the drawing the peculiarities of the motion. At A, the velocity of the pencil was directed upwards, at B it was greater, at C it was 0, at D it was directed downwards, at E it was again 0. At A, B, D, E, the acceleration was directed upwards, at C, downwards. At C and E it was greatest. The summary representation of what Galileo discovered is best made by a table of times, acquired velocities, and traversed distances. For time 1, the velocity is g and the space is 1 squared times g over 2. For time 2, the velocity is 2g and the space is 2 squared times g over 2. For time 3, the velocity is 3g and the space is 3 squared times g over 2, and so forth. In general, for time t, the velocity is g times t and the space is t squared times g over 2. But the numbers follow so simple a law, one immediately recognizable, that there is nothing to prevent our replacing the table by a rule for its construction. If we examine the relation that connects the first and second columns, we shall find that it is expressed by the equation v equals gt, which in its last analysis is nothing but an abbreviated direction for constructing the first two columns of the table. The relation connecting the first and third columns is given by the equation s equals gt squared over 2. The connection of the second and third columns is represented by s equals v squared over 2g. Of the three relations, v equals gt, s equals gt squared over 2, s equals v squared over 2g. I may add a remark in connection with this table that is very valuable. It has been stated previously that a body, by virtue of the velocity it has acquired in its fall, is able to rise again to its original height, in doing which its velocity diminishes in the same way with respect to time and space as it increased in falling. Now, a freely falling body acquires in double time of descent double velocity, but falls in this double time through 4 times the simple distance. A body, therefore, to which we impart a vertically upward double velocity will ascend twice as long a time, but forms as high as a body to which the simple velocity has been imparted. It was remarked very soon after Galileo that there is inherent in the velocity of a body a something that corresponds to a force, a something, that is, by which a force can be overcome, a certain efficacy, as it has been aptly termed. The only point that was debated was whether this efficacy was to be reckoned proportional to the velocity or to the square of the velocity. The Cartesians held the former, the Leibnizians the latter. But it will be perceived that the question involves no dispute whatever. The body with the double velocity overcomes a given force through double the time, but through 4 times the distance. With respect to time, therefore, its efficacy is proportional to the velocity, with respect to distance to the square of the velocity. D'Alembert drew attention to this misunderstanding, although in not very distinct terms. It is to be especially remarked, however, that Huygens' thoughts on this question were perfectly clear. The experimental procedure by which, at the present day, the laws of falling bodies are verified is somewhat different from that of Galileo. 2 methods may be employed, either the motion of falling, which from its rapidity is difficult to observe directly, is so retarded without altering the law as to be easily observed, or the motion of falling is not altered at all, but our means of observation are improved in delicacy. On the first principle, Galileo's inclined gutter and Atwood's machine rest. Atwood's machine, shown in figure 97, consists of an easily running pulley over which is thrown a thread to whose extremities 2 equal weights P are attached. If upon one of the weights P we lay a third small weight P, uniformly accelerated motion will be set up by the added weight, having the acceleration open parentheses P over 2P plus P close parentheses G, a result that will be readily obtained when we shall have discussed the notion of mass. Now, by means of a graduated vertical standard connected with the pulley, it may easily be shown that in the times 1, 2, 3, 4, and so forth, the distances 1, 4, 9, 16, and so forth are traversed. The final velocity corresponding to any given time of descent is investigated by catching the small additional weight P, which is shaped so as to project beyond the outline of P, in a ring through which the falling body passes. The apparatus of Morin is based on a different principle. A body to which a writing pencil is attached describes on a vertical sheet of paper, which is drawn uniformly across it by a clockwork, a horizontal straight line. If the body fall while the paper is not in motion, it will describe a vertical straight line. If the 2 motions are combined, a parabola will be produced, of which the horizontal abscissae correspond to the elapsed times and the vertical ordinates to the distances of descent described. For the abscissae 1, 2, 3, and so forth, we obtain the ordinates 1, 4, 9, 16, and so forth. By an unessential modification, Morin employed, instead of a plain sheet of paper, a rapidly rotating cylindrical drum with vertical axis by the side of which the body fell down a guiding wire. A different apparatus, based on the same principle, was invented independently by Laborde, Lippisch, and von Babbo. A lamp-black sheet of glass, shown in figure 98a, falls freely, while a horizontally vibrating vertical rod, which in its first transit through the position of equilibrium starts the motion of descent, traces, by means of a quill, a curve on the lamp-blacked surface. Owing to the constancy of the period of vibration of the rod combined with the increasing velocity of the descent, the undulations traced by the rod become longer and longer. Thus, in figure 98, BC equals 3AB, CD equals 5AB, DE equals 7AB, and so forth. The law of falling bodies is clearly exhibited by this, since AB plus BC equals 4AB, AB plus BC plus CD equals 9AB, and so forth. The law of the velocity is confirmed by the inclinations of the tangents at the points A, B, C, D, and so forth. If the number of oscillations of the rod be known, the value of the acceleration of the rod in experiment of this kind may be obtained. For more exact measurement of minute portions of time, a rapidly operating clockwork, called a chronoscope, is set in motion at the beginning of the time to be measured and stopped at the termination of it. Hipp has advantageously modified this method by simply causing a light index hand to be thrown by means of a clutch in and out of gear with a rapidly moving wheelwork regulated by a vibrating reed of steel tuned to a high note and acting as an escapement. The throwing in and out of gear is affected by an electric current. Now if, as soon as the body begins to fall, the current be interrupted, that is, the hand thrown into gear, and as soon as the body strikes the platform below, the current is closed, that is, the hand thrown out of gear, we can read by the distance the index hand has traveled the time of descent. Among the further achievements of Galileo, we have yet to mention his ideas concerning the motion of the pendulum and his refutation of the view that bodies of greater weight fall faster than bodies of less weight. We shall revert to both of these points on another occasion. It may be stated here, however, that Galileo, on discovering the constancy of the period of pendulum oscillations, at once applied the pendulum to pulse measurements at the sickbed, as well as proposed its use in astronomical observations and to a certain extent employed it therein himself. Of still greater importance are his investigations concerning the motion of projectiles. A free body, according to Galileo's view, constantly experiences a vertical acceleration g towards the earth. If at the beginning of its motion it is affected with a vertical velocity c, its velocity at the end of the time t will be v equals c plus gt. An initial velocity upwards would have to be reckoned negative here. The distance described at the end of time t is represented by the equation s equals a plus ct plus 1 half gt squared, where ct and 1 half gt squared are the portions of the traverse distance that correspond respectively to the uniform and the uniformly accelerated motion. The constant a is to be put equal to 0 when we reckon the distance from the point that the body passes at time 0. When Galileo had once reached his fundamental conception of dynamics, he easily recognized the case of horizontal projection as a combination of two independent motions, a horizontal uniform motion and a vertical uniformly accelerated motion. He thus introduced into use the principle of the parallelogram of motions. Even oblique projection no longer presented the slightest difficulty. If a body receives a horizontal velocity c, it describes in the horizontal direction in time t the distance y equals ct, while simultaneously it falls in a vertical direction the distance x equals gt squared over 2. Different motion determinative circumstances exercise no mutual effect on one another, and the motions determined by them take place independently of each other. Galileo was led to this assumption by the attentive observation of the phenomena, and the assumption proved itself true. For the curve which a body describes when the two motions in question are compounded, we find, by employing the two equations above given, the expression y equals the square root of open parentheses 2c squared over g close parentheses times x. It is the parabola of Apollonius having its parameter equal to c squared over g and its axis vertical as Galileo knew. We readily perceive with Galileo that oblique projection involves nothing new. The velocity imparted to a body at the angle alpha with the horizon is resolvable into the horizontal component c cosine alpha and the vertical component c sine alpha. With the latter velocity, the body ascends during the same interval of time t, which it would take to acquire this velocity in falling vertically downwards. Therefore, c sine alpha equals gt. If onward, it continues its motion as a horizontal projection. If we examine any two epochs equally distant in time, before and after the transit through S, we shall see that the body at these two epochs is equally distant from the perpendicular through S and situated the same distance below the horizontal line through S. The curve is therefore symmetrical with respect to the vertical line through S. It is a parabola with vertical axis and the parameter open parentheses c cosine alpha close parentheses squared over g. To find the so-called range of projection, we have simply to consider the horizontal motion during the time of the rising and falling of the body. For the ascent, this time is, according to the equations above given, t equals c sine alpha over g, and the same for the descent. With horizontal velocity c cosine alpha, therefore, the distance is traversed. W equals c cosine alpha times 2c sine alpha over g equals c squared over g times sine alpha cosine alpha equals c squared over g times sine 2 alpha. The range of projection is greatest accordingly when alpha equals 45 degrees and equally great for any two angles, alpha equal 45 degrees plus or minus beta. The recognition of the mutual independence of the forces or motion determinative circumstances occurring in nature, which was reached and found expression in the investigations relating to projection, is important. A body may move, as shown in figure 101, in the direction AB, while the cause of the motion occurs displaced in the direction AC. The body then goes from A to D. Now, this also happens if the two circumstances that simultaneously determine the motions AB and AC have no influence on one another. It is easy to see that we may compound by the parallelogram not only displacements that have taken place, but also velocities and accelerations that simultaneously take place.